Okay, the first thing I want to do, actually, besides advertise the book, um, is to give folks an opportunity to thank all of the Tamarisk Coalition folks that made this conference happen, particularly Kara. Is Kara in the room? Ah, well, let's give them all a big hearty applause anyway. I had written everybody's name down so I wouldn't forget anybody, but then I left it on the table over there. Okay. Hello? I don't know what happened. Next slide. There we go. Okay. So the research that I'm showing you is a part of our work with the Dolores River Restoration Partnership. And then at the end, I'm going to talk about some work that it uses those data, but also a lot more data. That is work by my postdoc, Eduardo Gonzalez, who's in France currently. So I always like to start with acknowledgments. Particularly, we thank the Tamarisk Coalition and Julie in particular. And we had a lot of different funding sources. We're really grateful for all of the support over the years. And of course, none of this can happen without painstaking work by field folks. Primarily for the data that I'm going to be showing you today, it's Rob Anderson and Hisham Elwire and Annie Henry. And Rick was great too. So we know that usually our goal for tamarisk removal is to produce an ecosystem with a lot of natives in it. But we also know that the results of tamarisk removal are highly variable. These are each representing a site that Robin Bay, one of my graduate students some years back, measured native cover at, with the x-axis being, okay, this is time since tamarisk's removal. And we can see it's all over the map, right? So can we understand why some sites do well and other sites don't do well? And does it matter, specifically for the work I'm going to show you today, how we remove the tamarisk? So the Dolores River Restoration Partnership established 40 sites along the Dolores River representing 4 different field offices. And we monitored these using point intercepts along lines for over a span of 5 years. Now these different sites represented 3 possible scenarios. They could have been hydroaxed, which we called mechanical only, or they could have had cut stump removal, which we called, or actually it wouldn't be mechanical only, it would be mechanical plus biocontrol, because there's biocontrol everywhere. Or you could have biocontrol plus mechanical, this is a mechanical approach here, and chemical and cut stump method, or just biological control. So we want to see what do the trajectories look like over time of the plant communities with each of these methods. Oh, and importantly, we called the mechanical plus biocontrol and the cut stump plus biocontrol our active removal methods, and we will refer to that terminology later, like this slide. So what we saw, if we are looking at the 2 axes here, this is looking at the efficacy of these methods for removing the tamarisk, because our y-axis is percent cover tamarisk, and we have our three of our sampling periods at 2-year intervals on our x-axis. And what we can see is that, of course, we're not surprised, with both cut stump and hydroax, the cover declines rapidly, right? This is before and this is after. The control in many cases happened in 2011, in some cases in spring of 2012, but in any case, and more sites had more removal even here, so we see this dramatic decrease. In contrast with the biocontrol only, where it looks like maybe we even have an increase in cover. Well, we did see more young individuals coming in at these sites, but Oh, and these are the statistics if anyone doubts that these are different. Multiple, it's a repeated measures ANOVA. But it's not that biocontrol is so bad as that looks, because those measures was just, is there tamarisk there? Because my field hands did not feel comfortable saying, is it alive, is it dead? Because it can look dead, but it's not, it's just defoliated. But in 2014, I asked them to distinguish between whether there were leaves on it or not. And you can see that even though the biological control only site did have more green cover than did either of the other two, it's not by a whole lot. And the vast majority of that cover is dead, or at least the branches appear dead. We can also see the difference between the sites where cut stump was used versus mechanical control, and not surprising, in adding that herbicide component did help reduce tamarisk cover. But what about what was going on with the native species? Because that's really the point of what we're doing here. Now, I might have shown this graph a few years ago, which was early on, where we just had 2010, 2012, 11, which isn't on here, and 2012, where I've lumped together both of the active removal types and looked at it in comparison with the beetles only. One thing that's really important to note here and shows why you need change over time is that where the sites were chosen to do the active removal wasn't random. They started out doing better in understory native cover than the beetles only. But if we're looking at rate of improvement over time, we can see they both improve, but those where there's active removal had a quicker or more dramatic improval over time than the beetles only. But look what happens when we add 2014. What was so interesting here is that although there was a difference in native understory cover at this point, they converge in 2014, such that it didn't matter whether the tamarisk was taken down by active removal or just biocontrol. The native cover it had increased over time in all sites, and actually had increased a little bit more dramatically between these two time periods than in the active removal sites. So this is great news, I think, for biocontrol, that there wasn't a big difference here. So we can see that dramatically understory native cover did increase over time, and that had to do with a lot of hydrological stuff too. But that's total cover, and total cover gives us one metric that is of interest, but we also need to look at relative cover. So I've made a little drawing here to illustrate why. These two plots have the same total cover, if the green is native, but if we consider how much exotic stuff is there, then we really need to consider the relative cover. This site looks a lot better, right, than this one. But if we just looked at total cover, we wouldn't be able to discern that difference, right? So when we look at our data in terms of relative native cover in the understory again, it looks a little different. What we see, again, is that the starting point is different, that the cut stump were established in sites that look the best. But what's interesting about the cut stump sites is, yes, they increased in relative cover of natives after removal of tamarisk, but then in 2004, it goes down. Why? Because there are more exotics. So the exotics are increasing over time also, and for the cut stump sites, they're increasing more. Trackhoe also has that triangle shape going on, not quite as dramatically, but trackhoe or mastication. But biocontrol is just keeping to look good. So in this case, we're not seeing the exotics going crazy in the biocontrol sites, which I think is really interesting. We're going to come back to why that might be. And here are the stats for this graph. So to summarize the Dolores River results, we found that the native cover is increasing over time in the Dolores, and that although it looks like biological control is slower, in the long run, it may have similar or even better outcomes than the more active removal approaches. Okay, so now Eduardo Gonzalez. Several of you know him. He's a great guy who wanted to be here but couldn't. So I'm going to give a little bit of his talk, which is collaborative work that he did with me and with a bunch of other people. What he did is basically go through my Rolodex and then some to collect data that people had taken at restoration sites across the West. So there are more than 400 sites. Many of these were tracked over time. Some are active restoration sites, others are not. So it gives us tremendous power to be able to see how broadly applicable the things that we're seeing just along the Dolores, for example, are to the entire western United States. So this is a map of all the sites that we were able to compile data for. They include 3 categories. We have reference sites called undesirable reference sites. That's where there's just tamarisk and nothing's been done to it. We have the favorable, the desirable reference sites. Those are where there's beautiful riparian native community going on. And then we have places where active restoration was done. And incidentally, those categories of desirable and undesirable, we let the managers tell us. So it's what they considered for their project to be the positive reference or the negative reference. That wasn't something that we made a decision about. So I was glad to see that several folks over these 2 days have presented ordination results, but I know that most people, including me as of a few years ago, get headaches looking at these things. So I'm going to try to make it as clear as I can without spending too much time on it. Basically, what an ordination tool allows you to do is have as a dependent variable a whole lot of stuff at once. And in this case, the whole lot of stuff is the entire plant community. So rather than just looking at, as I did in the other graph, just Tamarisk's response to restoration or native plants all lumped in one category as our dependent variable, here we have all the species that have been recorded at all of these sites. And what it does is it boils it down into these new vectors. And we've chosen the first 2 vectors, this one and this one, to plot all of our sites on. And what we could tell looking at how each species was weighted in that new vector, that we can consider vector 1 in terms of if it had a low value of this vector, then it was more likely to be a monoculture of tamarisk. And we can see that that's where tamarisk falls out, so that's how we made that designation. The other end, we have populus, that is cottonwood, so gallery forests are over here. And in here we have mixed stands. So if a site had a value that was near 0, it meant that it had both tamarisk and populus in there. So I hope that's sort of intuitive. And then our second vector, really we ended up being able to look at it in terms of exotic versus native with Russian olive and Russian knapweed and kochia and tamarisk. There's populus down here too, but most of the species that had lower values were exotic species, and then you have willow up here, and there's some other native species that I'm not showing on here because we had literally hundreds of species in this analysis. Made the larger the value, the more likely it was dominated by native species. We also, then the value of this, we can do all kinds of things with this now. We can look at how the distribution of species, how the distribution of the sites according to their species relates to other variables associated with those sites. And what that showed us, for example, is that, for example, EC is electroconductivity or salinity. We saw that sites that were more saline were more likely to be monoculture tamarix, not surprising. The hotter sites were also more likely to be monoculture tamarisk. And then we have when there's more precipitation, average precipitation in a year, it's more likely to be a populous site. Along the native exotic, when there was more grazing, we saw more exotic, and so forth. So we can look at the relationships between these variables and the entire plant community, not just one species at a time. Another thing that we're able to do is look at where different regions fall out. So these are ellipses that represent where the sites that were along the Rio Grande were over here. The lower Colorado River Basin were up here, and the upper Colorado River Basin over here. Notice that there's a lot of overlap, but these regions definitely have some different plant communities going on. Another thing that we can do with the same two axes of the monoculture to gallery forest and the exotic to native going on up here is we can put in the centroids for each of our removal methods to give us information about the relationship between plant communities and removal methods. And to walk you through some of this, we have these desired reference sites, again, as designated by the land managers, being, not surprising, more native than exotic. It's way up here. It's not necessarily, notice, way over here with gallery forest, because that's not even an option, obviously, in a lot of places. But what was also interesting is that where the tamarisk was cut, or cut with herbicide application, were generally closer to the desired site than some of the other methods. But we have to keep in mind, we know from the DRRP data that that is also a function of the fact that you can't do cut stump method in a place that is miles and miles of monoculture tamarisk, right? It's just not feasible. So you're usually starting with a site in a slightly better state. So we have to be careful about how we interpret these data. And similarly, the biocontrol only sites tended to be exotic dominated and monoculture tamarisk. Why? Because that's one of the reasons why we do biocontrol. It can take care of those endless thickets that are just not feasible to do other active removal methods. So another thing that we're doing with these data is looking at secondary invasion and how that's affected by removal method. I know there is a lot to look at in this graph. Eduardo is famous for his super dense graphs that are not good for presentations, great for a paper that you can sit down and really spend time on it. But what I want to show you here is what we're looking at on our y-axis is Russian knapweed response against time since tamarisk removal. Now, he lumped together different removal methods based on how disturbing of the ecosystem it is. Because there's a general ecological assumption that with more disturbance, you're going to have more weeds. Well, if we, as it turned out with Russian knapweed, at low and medium disturbance, with time, it increased. That was a problem. But if you look at the far out time periods here, that was really only true of the medium and low, that in fact, high disturbance sites didn't have more, had in general less Russian knapweed than the less disturbed. So we're talking about this is going to be cut stump down in here, and this is going to be heavy machinery up in here. And what was so fascinating is we saw the opposite results with kochia, which won't be a surprise to some of you here. But we saw no relationship with time. There were no significant patterns across time. But in general, we saw that the more disturbed the site was, the more ripped up it was with heavy machinery, the more kochia it had, but that these patterns were only true in the early years and disappeared in the later years. There's a slight trend for it, but in general, those are going to be the most dramatic in the first few years after tamarisk removal. So to summarize the whole thing here, removal method matters, right? We see that it matters for tamarisk control in the short term, but we'll see for the long term. It might not matter so much for understory native cover, and it has different effects on the secondary invasion depending on what weed you're looking at. So you need to make a decision about what are you more afraid of, kochia, Russian knapweed, and we did this with a bunch of other species as well. So you have to look for that publication. So with that, I will say thank you. And before we do questions, we're going to do the drawing for the book. So if I could have Annie bring me the little cup that's there. So this is for folks who are willing to give up some time to interview and know that if you didn't get in on this, please email me. We would love to hear from you. We're really interested in how oh, where is the cup with the thingies in it? Oh, okay, we'll do the drawing later. Let's do questions.
I have two questions. One is, where was the Russian knapweed biocontrol relative to the sites that you were monitoring Russian knapweed? And two is, on your fourth year of kochia monitoring, is it chance that it was just like a dry year and you didn't have as much seed germination?
So that's a great question. The power of these data is this spans decades of monitoring in different sites all over the place. And so thank you so much. As we dig deeper into this, we'll be able to determine the extent to which we have relationships with drought and like kochia. Oh, I was going away. I was going to show you. If you remember the ordination that I first showed, where kochia was, kind of near tamarisk, that was a sector that was drier. So yes, I think that could be absolutely a factor. And then what was your first question? Can you repeat that?
The relative location of the Russian knapweed biocontrol to the Russian knapweed sites you were looking at.
Great question, and we haven't looked at that yet, but we definitely should. If no other questions, thank you very much. Oh, yes. Okay, go ahead. You can tell it's the end of the conference, right? We're all just a little off our game. Okay, so now I'm going to pick the lucky winner of the book, and the lucky winner is Katie Fitzgerald. Katie, are you in here? Yay, Katie! Woo! And thank you all who participated in the interviews.